Hello. Make sure everything looks okay. Okay, so good morning, everybody. So just want to make sure I see here we have two students. Can you hear me?
Yep.
Okay, great.
Yeah.
So last time I explained that we have different systems for numbers like decimal, binary, octal, hexadecimal. And also I explained how can we do conversion between them, okay? So, and also I explained why we need these different, in almost all classes you took so far in your life, we only use decimal numbers. I guess in most classes we only use decimal numbers. So why in this course I'm teaching other systems simply as I said last time, because humans we use decimal numbers, but computers are using only binary numbers, ones and zeros, as you will understand better in this course. And for hexadecimal and octal, if I want to give you a number in binary, it's more convenient to give you the number in hexadecimal than binary. That's it. And it's easy to convert hexadecimal to binary or binary to hexadecimal. And hexadecimal is very short. So as I explained last time, every 4 binary digits are going to be represented by only 1 digit in hexadecimal. Okay. So actually, so hexadecimal is just as I told you. If I want to tell you in the memory location we are storing, for example, 3A hexadecimal. Okay. That doesn't mean the memory is storing exactly 3A as hexadecimal, because memory, like any digital system, it's only it only works on binary numbers. So I mean, what is stored in the memory location is actually this number, but in binary. But it's just easy for me to tell you 3A than giving you just a bunch of ones and zeros. That's it. Okay. Anyway, so I explained all of that. How can you do conversion? And then after that, I explain in binary number, how can you do addition? How can you subtraction? After that, I move to how can we represent positive numbers and negative numbers. I want you to understand this is different from the decimal number we are using. In decimal number, I can say positive 3 or 3. Both of them is the same thing. It means positive 3. If it is negative, so I'm going to say negative 3. So we put here a special sign to indicate if this number is positive or negative. That's what we do in decimal number. However, in binary numbers, we cannot do that. Why? Because it's not, keep in mind what this course is about. This course is about how can we do operation by hardware. Okay, that's what you will see in this course. Okay, because in any computer system or a digital system, okay, everything has to be executed by the hardware. So you write your program in C language, in Java, in Python, whatever the language you are using, okay? No one care about this language, or the hardware doesn't care about what language you are using, because we need to use compilers. These compilers have to translate your language to the machine language, okay, or assembly language. The machine language, okay, in the machine language, there are hardware. They are executed by the hardware, okay? So every instruction in assembly or in a machine language actually has a hardware that can do this instruction. So that's what you have to keep in mind. Any program you write, okay, at the very end, it has to be executed by the hardware, okay? So let's return to my point here. My point here, for hardware, it's not convenient. It's not to use a symbol like this one to represent positive and negative number. Instead, we are going to do something different. So what we do here to represent positive and negative numbers is, but before I give you details, as I told you last time, if you have any bit number, okay. So in this any bit number, we can have up to n to the power n different combinations of these numbers, okay. I call it the space. This is the whole space we have. I give you a simple example. So if the n bit here, if n is equal to 2, okay, that means we have four different numbers, or we have four different combination, which is, for example, 0 0. This is one combination, 1 1 0 and 0 0. Sorry, 1 1. So these are all possible cases here, okay? Same thing, if n here is 3-bit, in case of 3-bit, so we have 2 to the power of 3, which is 8 different combination out of 3 bits, and so on. So this is general for any n. This is a different combinations we have, okay? So what we do is, again, as I told you, we don't use a sign like positive and negative. Instead, what we do is, I divide this space or this combination. I take half of them, okay, or part of it I consider it positive, and the other part here I consider it negative. Is that okay? And the way this is, I'm going to give you more details to understand, but what you should understand now, the story here is different from the decimal point. We are not going to represent positive and negative numbers. We're not going to put sign like positive or negative. Instead, the whole space I have, I'm going to split this space between, so some numbers here are positive or some numbers here are negative, okay? I'm going to give you more details about this, but before I give you details, also last time I made definition. The definition is about the first complement and second complement, okay? So there is something we call it first complement. Oh, and also we have something we call second complement. Sometimes I call it second, or sometimes we call it two's. It's a two's complement. It's coming from number 2, two's complement, okay? So let's make a definition. So what is the one's complement and what is the two's complement? And then I'm going to tell you why we need them. As I explained last time, if I give you a number, a binary number, for example, if I give you a number like that in any binary number, 1 0 1 1, and then I ask you to calculate the ones complement of this number, okay? So I give you a number, and then I ask you to calculate the ones complement of this number, okay? Or the first complement. So all what you have to do is you just flip the bits. So actually here the ones complement here is actually 0 0 1 0. This is the ones complement. Is that okay? So if you calculate the ones complement of this number, you are going to go back to here. Okay, this is the ones complement. It's just a definition. What you need to know here is, I'm going to ask you why we need it. That's a different story. Okay, but for now, it's just a definition. If I give you a number and ask you to calculate the first complement or ones complement, this is how can you calculate it, okay? What it means, that's what I'm going to explain for sure. Now, how can we calculate the two's complement or the second to complement, second or two's? Okay, so what you have to do first, you have to calculate first the first to complement this way, and then you have to add number 1. So if I add 1 here, it becomes 1 0 1 0. So this one here, from here to here, this is the second to complement. If you calculate the second complement of this one, you come back to here, okay? Any question regarding this point? So the ones complement, guys, very simple. You just flip the bits. Very simple. Flip the bits. The second complement is actually the first complement, and then you add 1. Okay. So this is just definition. But now, when I in this slide, when I explained about positive and how can we represent negative and positive numbers in binary, I told you, first of all, I told you there are different systems, okay? So we have a system called the signed magnitude, we have signed first complement, and the signed two's complement. But I'm not going to waste the time talking about these two. I'm going to focus on this one, simply because almost all digital systems now are using this one, okay? Why? Because as you will see in this course, it is just hardware, it's hardware friendly. That means you can do the calculations addition, whatever the multiplication, using less complex hardware. Okay, that's why it's more efficient to use this one. That's why I'm gonna focus on this one. Is that okay? So what this one is telling me is, okay, so is if you want to calculate the two's complement is used if you want to multiply a number by -1. For example, okay, so this is +7, okay, which is this one. Is that okay? So if you calculate the two's complement of this one, you are gonna get -7, which is this one here. Okay. So if you calculate the two's complement of this one, you are gonna come to here. So if you have a number and you calculate this number, you calculate the two's complement of this number, the result is similar. It's like you multiplied by -1. So if it is 7, it becomes -7. If it's -7, it becomes +7. This is true for any other number. We can try if you let's try. For example, this number 3. Okay. Let's calculate the two's complement of this one. I'm sure it will be this one. Okay, but if I'm correct, let's see. So in order to calculate the two's complement of this one, number one, you have to calculate the first complement, which means you have to flip the bits. Okay, and then after you flip the bits, you have to add 1. So now it becomes 1 0 1 1. So this one here is actually the two's complement of this one. Okay, and the opposite, and this one is the two's complement of this one. Don't be confused. So if you calculate the two's complement of this one, you are gonna come here. If you calculate the two's complement, you come here. So if you see, this is the same thing like -3 here. Is that okay? So now to make it easy, what we are gonna do here is, look here. As I told you, the whole space in case of 4 bits, as I told you, in case of 4 bits. So now how many combination you can have? 2 to the power of 4, which is 16. So I'm gonna take part of this combination. I'm gonna consider it positive numbers. I'm gonna take another part. It will be negative numbers. Okay. So how can you tell? Very simple. So these are the negative numbers here. If the last bit is 1, so this is negative number. If the last bit is 0, okay, so this is a positive number. Is that okay? So all what I did, I just took the whole space, I split it between positive and negative number. Okay. And last bit here in this case, we call it the sign bit because this one can tell me, okay. But I'm sure students are confused here, or sometimes they are confused. It's not like positive and negative. So instead of positive, I'm gonna put 0. Instead of negative, I'm gonna put 1. No, I didn't say that. I said, okay, yes, the last bit can tell you if it is positive or negative, but the way you have to calculate the negative numbers is, first you have to calculate the positive number, and then you calculate the two's complement of this one. Okay, let me be clear here. So if, for example, in exams, in anything, if I tell you, okay, can you give me +5? Okay, this is similar to what I explained last time. For example, I'm gonna assume we have 4 bits, okay, in case of 4 bits. So +5 should be 1 0 1 0. Is that right? Because this is the weight of this one is 1 2 4 8. Okay, so this gives you +5. Okay, so if I ask you to give me the positive number, this should be easy, similar to what I explained in before. You can divide it by 2. You can keep dividing by 2 as I explained by 2, but here I didn't divide by 2 because this is easy. I can guess it from the weight. You got what I'm saying? But as I explained last time, you can keep dividing by 2 and then you can get the number here. So this is for positive. So any positive number, you can get it this way as I explained it before. Now the question is, if I ask you to give me -5, okay? So the way you have to do it is, or maybe there are different ways, but this is the easy way. The easy way is you can calculate +5 first, okay? And then you calculate the two's complement of +5. That's it. Okay, this will give you -5. Okay, so for example, here in this case, this is a +5. Then I'm gonna calculate the 1's complement 0 1 0 1 and then add 1. So this one should be -5. Okay, so this 100% this will be a question in quizzes, anything. I'm gonna ask you. Okay, for example, I'm gonna give you any number, like for example, give me +7. Okay, and then I'm gonna ask you, give me -7. Okay, so the way again for positive you can do it directly. Okay. For negative, you have first to calculate the positive number easily, okay, as explained before, and then you calculate the 2's complement of it to get -7. Okay. So this is how can you convert here. I did, if you see, I explained before how can you convert a decimal to binary, right? But now I did minor change than what I explained before. Okay. What I explained before, it was for positive numbers. So what I explained before, it was here. Okay. I just added one thing more. If you have negative numbers, you have just after you get this one, you need to calculate the 2's complement in order to get the negative number. Okay. Again, as I told you, if I give you a number, and then if you want to know if this number is positive or negative, you have to look at the most significant bit. You have to check the most significant bit, which is the last bit here at the left. If the most significant bit is 0, that means it is a positive number. If it is 1, that means it is a negative number. Okay. So I'm gonna now explain, or not explain. I'm gonna do a little bit of change to what I explained before. How can you convert binary to decimal or decimal to binary? Okay. So as I have just said right now, if I ask you, give me -7. Is that okay? So the way you have to do it, first you have to do +7, which is 1, 1, 1, 0. Okay. Here I'm asking you to store the number in 4 bits. Okay. Maybe I ask you to make it 8 bits or whatever, but here it's 4 bits. Okay. So just give me 1 second. Okay, so this is +7. You can get this one similar to what I explained before. You can divide by 1, or you can check the weights. So this is the weight of 1, weight of 2, weight of 4. 1 plus 2 plus 4 is 7. Okay, anyway. And then in order to move from here to here, actually you have to calculate the 2's complement, okay, in order to get -7. The 2's complement is actually the first complement. You just flip the bits and then you add 1. So this actually becomes -7. Okay. If you calculate the 2's complement of this one, you will come to here. Okay. So this is how can you convert a decimal to binary in case of signed number, if you have positive and negative. Okay. So now what if I give you a number and I ask you to now I want to explain the opposite. What if you have, okay, I'm gonna take the same example here. What if I give you a binary? So what I explained right now here, if the number is signed, how can you convert decimal to binary? Now I'm going to explain how can you convert binary to decimal. Okay, so look here. So if I give you a number like this one, 011. So this number, first of all, this number is positive or negative? It is positive. Okay, so because it is positive, you can use the same thing I explained before. Okay, it's the same thing I explained before. You have to multiply everyone by the weight. Here the weight is 1, weight of 2, weight of 4. So should be 4 plus 2 plus 1 should be 7. Is that okay? That's very easy. However, in negative numbers, if the number is negative, like for example 1001, this is a negative number. Okay, how I want to convert this negative number to decimal. How I can do that? Okay, so again, there are maybe different ways, but the way I like to make it is, so this one I'm sure it is negative, but I don't know what negative what. So this negative x. Is that okay? So the way I like to do it is, there may be other approaches, but the way I like to do it is, you just calculate the 2's complement. Once you calculate the 2's complement, you are going to have positive x. Okay. So let's calculate the 2's complement of this one. Should be 0, 1, 1, 0. This is the 1's complement. Add 1. So this is the 2's complement. Okay. So what it means? It means these two numbers are equal in magnitude, but this one is the negative version and this one is the positive version. Because this is a positive number, it's easy to read it using this approach. Okay, so I can read this one. This one is 7, so this one has to be -7. Okay, so let me tell you the conclusion here, because this 100% this will be a question in quizzes. Okay, I'm talking about now. If I give you a number, okay, if I give you a positive number, okay, decimal, how can you convert it to binary? This is similar to what I explained before. Okay, either you keep dividing by 2, or if it's a small number like this one, using the weights, you can get the number. Okay, but if I ask you to give me -7, So the way you have to do it, you have to do positive 7 because this is the easy way. And then you calculate the 2's complement of positive 7 to get negative 7. Okay? Now, the second part I'm explaining here is, what if I give you a number in binary and ask you to convert it to decimal? Okay, now there are two cases. If the number is positive, okay, so this is the same thing I explained to before. You have to multiply every number by the weight and then you add everything together. Is that okay? But if I give you a number in a negative number like this one, okay, don't read this one. Don't just put the weight, multiply the weight by the digits. That's wrong. That's wrong. Okay, so the way you have to do it, the easy way, in my opinion, to do it is, okay, this is a negative number. I can't read it by multiplying the weight by the digit. This is, I multiply the weight by the digit only in case of positive number. Okay, so I'm going to get the positive version of this number. Okay, and I convert this one. This one is 7, so this one should be negative 7. Okay, because the 2's complement, it means you multiply by negative 1. So if you have a number, whatever the number is, like for example 220, if you calculate the 2's complement of this one, you are going to get negative 220. Is that okay? So let me tell you the conclusion now. The conclusion, or the main thing we have right now, is what I'm saying. In case to represent a negative number in binary, we take the whole space. That's what we call the whole space. All different combination, and then almost half of this combination I'm going to use it for positive numbers, and the other half I'm going to use it for negative numbers. Is that okay? So now I'm going to give you a formula. I already give you one important formula. The important formula I already give you, and this is important. If you have n-bit number, how many combination you can have in n-bit number? 2 to the power of n. Okay, these are the different combinations. Now, if I have n-bit number, okay, what is the range of numbers I can represent in this n-bit number? What is the range of numbers I can represent? Okay, so actually it is, I told you I'm going to take half of these numbers, half of this one. Okay, half of this one is actually 2 to the power n minus 1. This is half. So here, so half, so this is the maximum negative number I can represent in this one. Negative 2 to the power of n minus 1. Okay, so I'm going to take half of one of them, and this one has to go all the way this is until the positive one is actually, it's not 2 to n minus 1. It's not. But wait a second, you told me you took the half for negative. Okay, so I should take the half of positive. No, don't forget there is a 0. Okay, that's why it should be 1 less. You can't split equally between positive and negative because we have 0 in the middle. Okay, so one of them should be greater than the other. So let me give you example. If n bits here are actually 3 bits. Okay, so in 3 bits, we can have numbers from 2 to the power of minus 2, 3 minus 1, which is actually minus 4. Okay, so this is the biggest negative number you can represent in 3 bits. The maximum one should be 2 to the power of 3 minus 1, negative 1, which is positive 3. So always the positive one is 1 less than this one. Yeah, I can give you another example. So if you think about 4 bits, for example. Okay, so it should be minus 2 to the power of 4 minus 1, which is actually minus 7. Is that okay? And then the positive one has to be, I don't need to calculate it because it's going to be the same thing, but 1 less. So positive 6. Okay, or as I said, a positive 2 to the power 4 n minus 1 minus 1. Okay, and that's exactly what we did here. So if you look here, I think something is wrong here. Oh, sorry, this is not negative 7. I'm sorry, this is negative 8, right? Because 2 to the power, and this is positive 7. I'm sorry, okay? So here, 2 to the power of 4 minus 1 is 2 to the power of 3, which is 8. And then, so if you have 4 bits, the range of numbers can be negative 8 to positive 7, okay? And that's exactly what we have here. So you see here, we have the biggest positive 7, the biggest negative is 8, okay? But keep in mind, still the combination, if you see how many numbers we have between positive 7 and positive 8, it is 2 to the power of 4. Because all what I did, this is the whole combination, the whole space we have. 2 to the power of 4, I just split it between positive and negative. Is that okay? Any questions? Okay. There is something also very important I want to talk about here. Numbers So numbers can be signed or unsigned. Okay, so here numbers, any number can be signed or unsigned. You remember in programming, when you define a variable, you can define if this variable signed or unsigned. Okay, unsigned means it's either 0 or positive. It can be negative. Sign means it can be positive, it can be 0, or it can be negative. That's the meaning of it. Okay, so like for example, if I want to define a variable, okay, to count the number of students in the class. For sure, this one can't be signed because this count of students or number of students in class cannot be negative. So it has to be unsigned. Does that make sense, right? But some other quantities, it can be signed, like the temperature today. Like temperature can be positive or it can be negative. Is that okay? So same thing, listen to me. Same thing here. We have numbers that can be signed or unsigned. And actually, we have different hardware to do that. So if I want to do multiplication, so we have a circuit, a hardware circuit for signed numbers. And then I have a hardware circuit for unsigned numbers. And when you take 3130, I used to teach 3130, okay, which is microcomputer system, which is assembly language actually. So when you take, remember, when you take 3130, you will find when you learn multiplication and division in assembly, you will see that you have different instruction for signed or unsigned numbers. Why? Because we have different hardware to do that. So when you write your program, you need to decide when you write your program if it is signed or unsigned, and then the compiler has to select which assembly language, which assembly code has to use, because I need different circuit for signed or unsigned. Is that okay? So now uh, uh, so now, how signed? I already explained signed. How unsigned would be different? Okay, it's very easy. It's the same thing. Look here, guys. If you have any bit number, so the whole space is in 2 to the power of n. This is the whole space. Okay. What I did in case of signed numbers, I actually split the whole space between positive and negative. Is that okay? But now I have only positive. I'm not going to split. That is why if you have in-bit number and this number is unsigned, okay, so actually it can represent the numbers from 0 until 2 to the power of n minus 1. Okay, so total here should be 2 to the power of n, because this is the whole space. So what happened here is I'm going to use the whole space for positive numbers. Is that okay? So let me, I think I have a summary here, very important summary. I think let me come here. Where is it? Yeah, here. Yeah, look here. This is very important summary to, so here, if you have an n-bit number, for unsigned number, it can go from 0 until 2 to the power of n. I think this is wrong. I'm going to correct it. I'm sorry. Yeah, it's good. Let me, yeah, I'm going to correct it. So this is actually 2 to the power of n minus 1. Okay, I'm sorry. Okay, because this is, if you put this way, you are going to use only half of the space. I have to use the whole space. Okay, so it should be from 0 until 2 to the power of n minus 1. I'm going to correct it. Okay, for the sign number, that's what I explained. From negative, I used almost half of the space in the negative one, half of the space in the positive one. So let's see, for example, here to understand exactly. This is very good example to understand exactly what I mean. Assuming we have 3-bit number, 3-bit. So in case of 3-bit, so this one should represent the numbers from 0 until 2 to the power of 3 minus 1, which is 2. Okay, which 2, so from 0 to 4. Okay, so that means the smallest number is this one is 0 all the way. I think something is wrong here. If you have 3-bit, yeah, no, it should be okay. No, 3-bit, 2 to the power of 3, so from 0 until yeah, it's correct. Okay, so it has to be, yeah, from here. No, but it has to be, I'm sorry. Oh, sorry. Okay. So actually, yeah, I said this is wrong. Okay. So it has to be 2 to the power of n minus 1 here. Okay. So actually, if you have 3-bit number, so it should be from 0 until 2 to the power of 3 minus 1, which is from 0 until 7. Is that okay? From 0 to 7. And So I use the whole space, okay? So, and this is exactly what you see here. So these are all the numbers we have, all the combination, okay? So this is 0, and then we have here 1. Look at the look at the inner one here. The inner one is for unsigned numbers, okay? So if you see here, I'm gonna get 1, 2, 3, 4, 5, 6, 7. So this number will be 7, okay? So if your number is unsigned, I'm gonna use the whole space for 0 and positive. So it's going to go from 0 until positive 7. However, if the number is signed, so I'm going to use the half of the space here and almost half the space in the positive and negative sign. Okay, so it will be negative 2 to the power of 2, 3 minus 1, all the way until 2 to the power of 2 minus 1, which is negative 4 until positive 3. Okay, and that's exactly what you see here. So what you see here in this example, you look at the outer numbers here, okay? Because this is for signed numbers, So if you see here, you can find this is 0, 1, 2, 3, okay, and 3, and this is actually the positive side. Now we start to have one here is the most significant bit. So this is the negative part. Okay, so half positive, almost half for sure. I told you there is one difference. Okay, unless you consider the 0 positive, that's okay. So here, so this is the negative side. So this one should be negative 4, negative 3, negative 2, negative 1. Okay, so for sure, there is no surprise that I can represent bigger numbers. Okay, so here I can go up to 7, okay? But here for positive, I can go only up to 3, okay? Makes sense, right? Because the whole space, because here I'm gonna go to until negative 4, okay? Yeah. So, okay, so let me tell you the conclusion. The conclusion is numbers can be signed or unsigned, okay? Regardless if the number signed or unsigned, 2 to the power of n give you how the combination or how big is the space or the different combination we can have, okay? And then if your numbers are unsigned, okay, so actually you can represent the numbers from 0 until 2 to the power of n minus 1, okay? But if you sign the numbers, so it should be from this negative until this positive. Is that okay? I know there is something always confuses students. Please pay attention to this one. It's confusing. That's why I want you to understand it. If I give you a number and I ask you if this number is positive or negative, how can you tell if the number is positive or negative? What you have to do, you have to look at the most significant bit, this bit here. As long as this bit is 0, so this number is positive, 0 or positive, okay? However, if it is 1 here, if the most significant bit is 1, so this bit, so this number is negative, okay? So you can tell from the number, when I give you a number, you can tell if this number is positive or negative easily, right? However, for signed or unsigned, there is nothing here can tell you if this number is signed or unsigned. Is that okay? So actually, signed or unsigned, this is something has to be decided by the programmer. As I told you, when you define your variable, you have to define your variable signed or unsigned, and then the hardware will give you two different circuits. One is going to do multiplication and one multiplication, but this is for signed, this is for unsigned. One, for example, is going to do division. This is for signed or division for unsigned. So it's going to give you two different circuits, and every one of them is going to have different instruction. Okay, in assembly. So what should happen is when you define your variable, the high level programming language has to decide when you convert it to machine code, should we use this hardware or this hardware? Okay, so let me say it again. If I give you a number, ask you this number is signed or unsigned, you have to laugh. Okay, because simply you cannot tell. Okay, so that's why the same number, look here, the same number can be 5 or can be -3. The same number can be 5 or -3. It depends if you consider it, okay? If you consider it signed or unsigned, okay? And this is something you can consider it during programming, okay? Same thing, this number, it can be 6 or it can be -2, okay? So, for example, if I did a calculation and I got a result and I want to display the result to the user, listen to me. If this is the result I got and I want to display it to the user, okay? So I can present, or I can show to the user 6, or I can show -2. Okay, so which one I have to do? This is something your program has to do it. Your program has to decide either it has to be 6 or -2. Okay, it depends on how you define the variable in your program. So, okay, so this is something can be handled in the program itself. Okay, so now. One more thing about the conversion here, because I have several examples before I go to these examples. Okay, so if I give you, and this is the important thing, look here, guys. If, for example, if I give you a number like this one, okay, and I tell you this number is unsigned. Okay, let me make it in a different way. Okay. Let me, okay. We agreed numbers can be signed or can be unsigned. Okay, we agreed on that. Okay. If it is unsigned, how can you convert a decimal to binary or binary to decimal? Unsigned. This is similar to what I explained before. For example, if you have 111 this way, okay, in order to convert it to decimal, okay, similar to what we did before, you have to multiply. This is 124. You have to multiply the weight by each one, so this should give you 7. Okay, so this is if it is unsigned. Okay, same thing. If I tell you you have 5. Give me the binary of 5. You just divide by 2. You divide by 2. So you're going to get, or 6, whatever it is, any number. So you have to keep dividing by 2. You will get something like 110. Okay. So this is similar to what I explained before. However, if the number is signed, now we have two cases. If the number is positive or the number is negative. Okay. If the number is positive, so I'm going to use the same rule like this one. Okay. So for example, if I have 0, 1, 1. Yeah, so all what I'm gonna do, this is the weight is 1, the weight of 2. Okay, so this one should be equal to 3. Okay. If I give you, for example, positive 5. Okay, so all what you have to, you just keep dividing by 2. Okay, so it should be 101. Okay, so if it is positive, negative is if it is signed and negative, this is a different case. Okay, so that's what I told you. So for example, if I give you a number like this one, okay, 111. Okay. Here, in case of unsigned, you convert by multiplying the weights because this number is negative. Okay, I know this is negative. Negative what? Okay, so don't multiply the weights. Okay, all what you have to, you can convert this one. You can convert this one to the positive version of it by calculating the 2's complement. So if you calculate the 2's complement, this is the 1's complement, and then you add 1. So this is number 1. Okay, so when I multiply this number by -1, I got +1. So this number should be -1. Is that okay? I give you several examples here. Hopefully it is clear. I know a little bit confusing, but if you have any question, just let me know. So I'm going to go through it again to see. Yeah, here I'm explaining how can you calculate the first complement, how can you calculate the second complement. Now, consider the number 9 represented in binary with 8 bits. So I want to store 9 in 8 bits. Okay. So the way you have to do it is, I have 8 bits here. Okay. So for sure you can keep dividing by 2, but for this small numbers, you can just consider the weights. So this is weight of 1, weight of 2, weight of 4, weight of 8. So if I put 1 at 8, 1 at 1, so I'm going to get 9. Okay. And I can store it in 8 bits. Okay. Someone should ask me, because this is a very important part. It may not be, it's somehow related to hardware. Okay. Someone can tell me, but wait a second, man, this is 9. So you should tell me just 1001. Okay. So why you put 4 zeros here? We know 4 zeros on the left, it doesn't matter. I fully agree. As a number, it doesn't matter. I fully agree. However, here I'm asking you to store it in 8 bits. Okay. So why you are telling me to store it in 8 bits? Because in hardware, we store it in a certain space. Okay, so I have a number, I store it in a register. A register is a hardware that can store numbers. So if this register is 8 bits, so even if the number is 91010, the hardware has to put something here, 000. You got what I'm saying? That's why here I'm telling you I want to store it in 8 bits because the hardware, you should put zeros here. But if you look at it as just a number, Okay, zeros on the left is not, it doesn't matter. That's I agree. But if you look at it as a number stored in a hardware, yeah. So the hardware has a storage unit or has a circuit for every bit. Okay. So these bits or the circuit, this circuit or the hardware circuit here has to store 0, 0, 0. Okay. Um, okay. Now if you look at this number here, I want to calculate -9, okay? And they store it in 8 bits, -9. Okay, so all what you have to do, as I told you, number one, you have to get +9, which is easy. And then once you get +9, I'm asking for negative. Okay, very simple. It's easy to get positive. So just get positive first, +9. And then after that, you can calculate the 2's complement. The 2's complement is the 1's complement first, 0, 1, 1, 0, and then 1, 2, 3, 4, and then you add 1. So it becomes this one. Okay. Any questions? If you have any question, just feel free to interrupt me. Now that's exactly what I explained. Maybe I just want to go through it because just examples. If I give you a binary number and I tell you this number is signed, okay. If I tell you this number is signed, okay. All what you have to do, if it is signed, but if this one is negative, like in this case, I look at the last bit here, it is negative number. Because this one is a negative number, I can't read it directly by multiplying the weight by each digit as I did before. Instead, you have to calculate the 2's complement of this one, and that's exactly what I did. So here this is a negative number, so I'm gonna get the positive version of this number. Okay, so I flipped all the bits first, and then I add 1. So this number and this number are the same, but this is a positive and this is the negative one. And then once you have the positive number, it's very easy to calculate it by multiplying the weight of every digit by the digit. Yeah. Also here I ask you, I need -5. Okay, convert it to binary using signed second complement. Okay, in exams I'm not gonna tell you. I'm gonna tell you just signed number, but I'm not gonna tell you it has to be second complement because this is the only thing we are gonna do in this course. Okay, and actually, as I told you, that's what most of the people are doing now. Okay, so first of all, if I want to do this one -5, okay, so it's easy for me to get +5. So this is a +5, and I store it in 8 bits. How did you know? The weight of this one is 1, 2, 4. Okay. If you are still confused, again, if this number is big number, I have to keep dividing by 2, as I explained before. But in case of small numbers, I can just guess. It's easy for me to guess from the weights. So I have to put here 1 at 1. 1 at 4, 4 plus 1 is 5. Okay, so this one is actually in order to get -5. So first I'm going to get +5, and then I calculate the 2's complement of this one by calculating the 1's complement plus 1. Okay, and then and this is the result here. So this is +5 and this is -5. If calculate the 2's complement of this one, you come here from. If you calculate the 2's complement of this one, you come from here to here. Yeah, that's what I'm explaining. Numbers can be signed or unsigned. I think nothing is new here. The most important part here, guys, and maybe I know it's maybe a little bit confusing, that the same combination, for example, look here, the same combination here, 110, the same combination, it can be +6 or it can be -2. If you consider this number unsigned, okay, or if you get this number from unsigned hardware multiplier or whatever, so this should be number 6. But if the numbers are signed, so it has to be -2. Okay. Yeah. So here, that's exactly what I'm saying. In case of unsigned numbers, you don't, in case of unsigned number, you don't have positive or negative, right? So all what you have to do, this is very straightforward. It's similar to what I explained before. You have to just multiply each digit by the weight and then add everything together. So if I give you this one here, you just multiply by the weight, add everything together. So this one will be 15. This one will be 7. Is that okay? However, if I give you the same number like this one here, but I tell you this is signed, not unsigned, okay? So you can see this is a negative number. Why? Because of the most significant bit here. This is a negative number. So this is negative what? Okay. It's easy for me to convert this one to the positive. So the equivalent positive one by calculating the two's complement. If you calculate the two's complement, first the one's complement and then you add one. So actually this is number one, positive one. Because this is positive one, so this one has to be negative one. Okay. But if I give you a number like this one, as you see here, for example, this is a positive number. In case of positive number, just similar to the unsigned, just read it directly by multiplying the weight by multiplying the weight by the digits and add everything together. In case of only negative numbers, this is the one you need to calculate the two's complement. Okay. Yeah, so here I'm giving you a number. I'm telling you this number is unsigned. Okay. Unsigned, for sure, there is no positive or negative. You don't need even to think about positive or negative. There is. Okay. So what you have to do here, just multiply everyone by the weight. So this is weight of 1, weight of 2, 4, okay, for 8 and 16. So this one should be 16 plus 8 plus 1, which is 25. Is that okay? Here I'm asking you the same number, right? The same number here. But I'm telling you, so if this number is unsigned, if this combined number here is unsigned, it should be 25 in decimal. However, if this number is signed, should be -7. Okay. I know maybe a little bit confusing. The same representation of bits can mean two things. It depends on if you are if your number signed or unsigned. Okay. So anyway, so if you have this number here, you can calculate again, because this number is negative. This number is negative. So in order to get negative what? Okay, so I need to get the positive version of this one by calculating the two's complement. To calculate the two's complement, first you have to flip the bits and then you add one. So this number is the two's complement of this number, or opposite of this one. So these two numbers are equal, but this one is negative and this one is positive. Okay, but I can convert the positive easily. Just this one multiply the weight, so this is positive 7, so this one should be -7. Any question, guys? So the conclusion is, if you have this number, if it is unsigned, so 25, if it is signed, should be -7. Any question? Okay, good. So now, the good thing I told you, the second complement, okay, is hardware friendly. Okay, it's hardware friendly simply because the main reason, and you will understand it better in this course later when I explain how hardware can do addition and subtraction. But the most interesting thing here for the two's complement, and that's the reason we use two's complement here to represent the negative numbers, is actually I don't need two different hardware circuits, one for addition and one for subtraction. I can use only one circuit, and that's what I'm going to explain later in too much details. I can use only one hardware circuit for addition and subtraction. Is that okay? So if I have an other, this other is actually adding just addition, okay? And here I'm inputting a number here. I'm going to call it number A. Here I input number B. Is that okay? And this is other. It's the same hardware. I can use it for subtraction. If instead of I input B, I'm going to input the second complement of B. You got what I'm saying? So A minus B, okay, is actually A plus second complement of B. This is why I can use the same hardware to represent to do addition and subtraction. Okay, because simply I can say subtraction is addition to the second complement. So instead, so very simple. So if I have two number A and B, if I input A and B, so now I'm going to do addition. However, if I input A and the two's complement of B, okay, so in this case, I'm going to have we're going to have subtractor. You got what I'm saying? I think that's what I'm explaining here. Let me see. By using two's complement, yeah, must, okay, addition of two So here, um, addition is similar to what I explained before. 1 plus 1 is 0, so there is no difference here. You got what I'm saying? For signed or unsigned. So either even if your number signed or unsigned, you can use the same approach I explained before to do addition. 1 plus 1 is 0, 1 plus 1 and 0, and there is a carry, some as I explained before. Okay. Now, yeah, so here, if I want to add two negative numbers, this is a negative number, okay? So what you have to do here, you just add similar to what I did before. No difference. If the numbers again, this also very interesting thing, by the way, in using second complement. So two interesting things here, guys. Number one, I can use the same hardware if numbers are signed or unsigned. I don't need two different hardwares. Okay, this is not the case in case of multiplication and division. When you take 3130, okay, remember when you take the assembly language, you will see for addition, we have only instruction for addition. Okay, the same instruction can be used for signed or unsigned. However, when you come to multiplication or division, you will find you have instruction for signed and you have another instruction for unsigned because it's different. Okay, but here in addition, this interesting thing here, I can use the same hardware to do addition of signed or unsigned. Also, I don't need new circuit for subtractor because subtraction is actually just addition with the two's complement. Okay, so what I'm saying here is, look here. For example, I have two numbers here. I want to add them together. Okay. So if I add here 1 plus 1 is, sorry, 0 plus 1 is 1, 1 plus 1 is 0, and then we have 1 here. 1 plus 1 is 0, and then we have 1 here. 1 plus 1 plus 1 is 1, and then you have 1 here. Okay. But in case of negative number, we just ignore the last one here, the last resulted from here. Okay. We don't take it as a part of the solution. Okay. So if you do that, you will get here, this is a -2 and -5, and I'm going to get -7 here. Okay. If I want to do subtraction this way of these two numbers, okay, so actually, so this way, how can you do it? Okay, very simple. So it's going to be -6, okay, plus 13. Okay. So here you have, you need to convert this. So for example, here, that's what I want to say here. What I want to say here is subtraction is actually addition to the two's complement. Okay, so this is -6, -6. Okay, represented in 8 bits, and this one is actually a -13. Okay, so in order to do this subtraction, all what you have to do, I'm going to do addition, but I have to calculate the two's complement of this one. So here, that's exactly what I did. So what I did here, I number one, I calculated the two's complement of this one, which was, yeah, I think this one here. Okay, so this one is the two's complement of this one, and then I added them together. Okay, so as I told you, A minus B is actually A plus the two's complement of B, which is B prime plus 1. You flip the bits and add 1. Okay, that's exactly what it is. So I took this number, I calculated the two's complement of this number, and then I added them together. I got this result here. Okay. Okay, so what I want to explain now here is something we call it extension. So what do you mean by extension? I'm going to tell you what I mean. So, but okay, so let me see, find some space here. Okay, look here, guys, extension. First, let's talk about unsigned numbers. Unsigned numbers. I told you in case of unsigned number, if you have n bits, you can store numbers from 0 until 2 to the power of n minus 1. Okay. For example, if you have here 4 bits, in case of 4 bits, you can represent numbers from 0 until 2 to the power of 15, right? From 0 to 15. Okay. So now, so what if your number is bigger? So you need bigger space. You need more bits. because 4 bits can store number from 0 to 15. If your number is 16, 17, whatever, you need a bigger number. But listen to me. When I say 4 bit can store up to 15, okay? That means it doesn't mean I can't store 15 in 6 bits, in 10 bits, in 1 billion bits. No, you can. But this is a minimum. Okay. So here the minimum to store 15. So 15 is actually 1, 1, 1, 1, 4 ones. Okay. So this is 15. The minimum space should be 4 bits. Okay. Can I store it in 5 bits? Yes. How I can do that? That's what we call extension. So extension means I have a number. This number is stored in 4 bits. Okay. And I want to store this number in a bigger space. That's the meaning of extension. So for example, 15 is 111. So this give you 15. Okay. So I store it in 4 bits. Can I store it in 5 bits? Yeah. So just put 0 here. Okay. So this is how I can store it in 5 bits. Can I store it in 6 bits? Yes. Just put 0 here. Can I store it in 7 bits? Yeah. Put 0 here. Can I store it in whatever bits? Yeah. Just keep putting 0s here. You are going to get the same number, but I just store the number in a bigger space. That's what we call extension. Is that okay? So what I'm saying here, if you have 4-bit number, I can store the same number in a bigger space, okay, by doing extension. Okay, so how can we do extension? Okay, so answer is now you have 2 different rules, signed or unsigned. Okay, in case of unsigned, you just put 0, 0 all the time. It's done. So if I give you a number and I ask you, and this will be also a question in the quiz, okay? I will give you a number, for example, stored in 8 bits or 5 bits, whatever, and then I tell you I want to do extension. I want to store this number in a bigger space, okay? So if this number is unsigned, so the question is, for example, I have 4 bits. Okay, so the 4 bits will be here. So the question is, what should I put here to get the same number? What should I put here to get the same number? So the answer is, in case of unsigned numbers, you have to put 0s to do extension. Okay, and this will guarantee you will get the same number, because I don't want to change the numbers. I want to get the same number, but I want to store it in a bigger space. Okay, so again, you can notice this is something not. I don't see 1111. I don't see it as a number. Okay, because if you see it like a number, okay, so it's 4 bits. Okay, so I'm gonna make it 4 bits. Why I put 0s here? Okay, so I see it like a number is stored in a certain space, in a certain hardware. You got what I'm saying? Because in numbers, in any number, doesn't make sense to put 0s on the left. 0s on the left doesn't matter, right? But here, because I'm focusing on the hardware, so if you store this one in a hardware, the hardware, we have a circuit for each bit. So you have to put something here. This circuit has to store something. So that's why you are going to put 0s here. Okay, so conclusion. If you have a number and you want to, I'm expecting now you understand what I mean by extension. Okay? Extension means you have a number and I want to store the same number in a bigger space, not smaller for sure, bigger space. Okay. For example, 4 bit, but I want to store this. I want to get the same number, but stored in 8 bits, in 16 bits, in whatever, but it has to be bigger than 4 bits. And what you have to do in case of unsigned numbers, the extension is done by adding 0s to the left. Case of unsigned number. Okay. Now, signed number is different. In case of signed numbers, now we have 2 different cases. If the number is positive or the number is negative. If the number is positive, which means the last bit is 0, extension is done by adding 0s to the left. Similar to the unsigned. The answer is yes, similar to unsigned. However, in case of negative number, okay, so the last bit is 1. If I want to do extension and I want to get the same number, because I don't want to change the number, so you have to put 1s here, not 0s. So in case of signed and negative number, 1s are not going to change the numbers. Okay, think about it. If you put 0, you are going to change the numbers, because the number is negative. You are going to make it positive. You are going to change the numbers. Okay, so conclusion. In case of unsigned, extension is done by adding 0s to the left. In case of signed, if it is positive, you add 0s. If it is negative, you add 1s. 1s is not going to change the number. I will convince you now. So in other words, you just repeat the same bit. So the same bit, you just repeat it here. You repeat the same bit here. Okay. So for example, let me tell you, for example, if you have this number 111, okay, this number is sign number is -1. Is that okay? So I want to store it in 4 bits. Okay. If I put 0 here, okay, if I put 0, this now becomes +7. So wrong. I changed the number. I don't want to change the number. I want to get the same number, but I want to store it in a bigger space. So what you have to do, as I told you, you have to repeat the same bit. Okay, so here you just add 1. If you add 1, if you calculate this number is still -1. If you add 1, so this is interesting somehow. So if you add 1 to the left, in case of negative numbers, okay, this is not, you are going to get the same numbers. It doesn't change the numbers because we are familiar with adding 0 to the left from the decimal numbers. From the decimal number, for example, I have 372. So if I put 0 here, it's not going to make a difference, right? But it's not true in case of negative numbers. So you have to put ones. Okay? So now I'm expecting, or I hope you understand what I mean by extension. You also understand how can you do it. Okay? So here, for example, I give you examples here. The unsigned, if I tell you unsigned, don't think about it. You are going to add zeros, unsigned, okay? So here I give you this number here, which is the number 15. So if I want to store it in 5 bits, I'm going to add 1 0 here. It's still 15. If you convert it, it will be also 15. And then I'm going to add 4 zeros here to store it in 8 bits. It's still 15. I didn't change the numbers, okay? However, in case of signed numbers, okay, so I have to put zeros in case of positive number. I have to put ones in case of negative number. Or in other words, to make it easy, just repeat the same bit. If the same bit is 1, just to do padding, we call it padding by the same bit, okay? So let's see, for example, here, this is -2, okay? Stored in 4 bit. So if I still I want to get -2 stored in 5 bit, just add ones here. Just add ones here. Once it's not, it's gonna get the same number. If you don't believe me, okay, I don't believe you. Okay, so I can prove it to you. For example, I claim this is -2, similar to this one. Okay, let's do the conversion. Convert it and see if it is -2 or not. First of all, this is 1. That means it is negative. Okay, to get the magnitude, so I'm gonna calculate the 2's complement as I explained before. I'm gonna calculate the 2's complement in order to I will calculate the 2's complement to get the positive version of it as I did before. So here it should be 1, okay? And then we have here 0, 0, 0, 0, 0, 0, 0, okay? And then I'm going to add 1. When you add 1 here, it becomes 1 plus 1, 0, 1, 0, 0, 0, 0, okay? So this number is actually 2, right? So it should be negative. If this number is 2, so this one should be -2, okay? Anyway. Any questions? Um, so now, just give me 1 second. Okay, so now I'm gonna move to another topic here. We'll call it overflow. Okay, so first of all, I want you to understand what I mean by overflow. Overflow, but before I explain it, let's agree on something I have already explained. Okay, if you have any bit, okay, you know from what I explained, there is a limit, and even that makes sense. There is a limit to the number I can store in any bits, right? So I told you in case of unsigned, you can store from 0 until 2 to the power of n minus 1. So you can't store more than 2 to the power of n minus 1. This is the maximum number you can store in any bits. In case of unsigned number, it's going to go from -2 to the power of n minus 1 until positive 2 to the power of n minus 1 minus 1. Okay? So this is the limit. So there is a limit. You understand what I'm saying? We agree on that. There is a limit. Okay. So now I want to talk about overflow. Look at the English word overflow. Overflow means you exceed the limit. Overflow means you exceed the limit. Okay. So what happens is that, for example, look here, guys. If I have a 4-bit number, 1, 2, 4, okay, you have 4-bit number, and I want to add it to a 4-bit number. I want to add 4-bit number to a 4-bit number. Is that okay? So if the result are more than 4 bits, needs more than 4 bits, that's what we call overflow happens. Again, I have a hardware circuit. This hardware circuit is adding 4-bit to 4-bit and store the result in 4-bit. Okay? If the result needs more than 4 bits, so in this case we say overflow happen. Okay? So why you may need more? Because you add. When I add number plus number, so actually the number can get bigger. Okay. So for example, let's have an example. In case of 4 bits, okay. Assuming it's unsigned, it's the same thing for sign, but I'm taking the unsigned here as an example to understand what I mean by overflow. Okay. So in case of unsigned, we agree we can store number from 0 until 15. Is that okay? So your limit is 15. Your limit is 15. So if I add 15 plus 10, so I need 25. You got what I'm saying? So that means I need to store it in more than 4 bits. Okay. But if the hardware is storing it in 4 bits, so you are going to get wrong result here because I need 5 bits. You understand what I'm saying? So again, I know what may be confusing you. What may confuse usually, if you look at it as numbers, you don't care about the space. You just add 1 plus 1. So for example, if you have something like that, you don't care, right? So 1 plus 1 is 0, and then we have 1. 1 plus 1, 0, and 3 ones here. 1, 1, 1, and then we have 1. So you just add 1 here. Okay, we don't care about the space. However, if you see it from the hardware perspective, I have here number in 4 bits. I have a number in 4 bits, and then the result is going to be stored in 4 bits. Okay, and because you do addition, it may happen that the number gets bigger, and the result needs more than 4 bits. Okay, in this case, you are going to get wrong result here. Okay, if you just look at the 4 bits here, you are going to get wrong result, and that's what we call overflow. Okay, so just a definition what is overflow. Okay. Now how can you know if I give you 2 numbers, signed or unsigned? How can you know if there is overflow or not? Okay, it's very simple. In case now I'm going to teach 2 different approaches. In case of unsigned numbers, okay, if I add 2 numbers together and there is a carry resulted from the last bit here, the most significant bit, there is a carry result from here. If the carry is 1, this can indicate that there is unsigned overflow. That means the result you got here, the result, if I add 4 bits plus 4 bits and store the result in 4 bits, the result here is wrong. Is wrong. You got what I'm saying? That as long as there is overflow, that means the result you get is wrong. You got what I'm saying? Because of the limit you have. Okay. So one more thing I want you to understand is if the 2 numbers, if I'm adding 2 numbers and they have the same sign, like positive or negative, I'm adding positive to positive or negative to negative, overflow can happen because the number is getting bigger. It may happen that you exceed the limit. However, if the 2 numbers have different sign, if the sign is different, I'm adding positive to negative, overflow cannot happen. Okay, but this by logic. Okay, so if overflow cannot happen in this case simply because the 2 numbers are not assisting. It's not getting bigger. Okay, they are not. This number I'm going to get here is going to be smaller than what I have here. Okay, so that's why the space should be enough. So let me say it again. If the 2 numbers you are adding have the same sign, either positive, negative, there is a risk that overflow can happen. However, if the sign is different, one positive, one negative, so in this case, overflow cannot happen. Okay, because you are making the number smaller, you're not making it bigger. Okay, so again, if your numbers are unsigned, And if you want to know if there is overflow or not, for sure there is a naive way to do it, a very naive way. You can, but it shouldn't be this way. Okay, you can look at the result. If the result is correct, if the addition is correct, if the result is correct, so that means there is no overflow. Okay, but it shouldn't be this way. I'm telling you a much easier way. The much easier way, if you do addition and then you find the carry here. Okay, you find the carry resulted from the last one. This is in case of unsigned numbers. If there is a carry resulted from the last one, so in this case there is overflow. Okay, but in case of signed numbers, I'm going to use a different approach. Okay, in case of signed numbers, if you add a positive number to a positive number and then you get a negative number, or I add negative number to a negative number and then I got a positive number. This is the only two cases I can get overflow. You got what I'm saying? You add positive to positive, you get negative. So all what you have to do is, in case of sign, just look at the sign bit here. If this one is negative, and then I got 0 here, so there is overflow. Okay. But if it is positive, I got positive, there is no overflow. If I got negative, and then I got negative, there is no overflow. So in case of signs, the only two ways you get overflow, when you add positive to positive, you get sign, or negative to negative, you get positive. Okay. So someone can ask me, what does it make any sense to add positive to positive? You get negative number. Does it make sense? For sure, doesn't make sense. Adding positive to positive should not give you negative. Yeah, I got negative because there is overflow, because the result is not correct. That's simple, right? So anyway, so here I explain too many things here regarding to this one here. So overflow means I'm going to add input number to an input number, but the result, it needs more space, n plus 1. This is a definition, okay? So in case of your numbers are unsigned, so if there is a carry, so just to do the addition, if there is a carry, there is overflow, okay? So let's for example, look at this example. I'm adding here, this is 5 bits. I'm adding 5 bits to 5 bits, and then I want to store the result in 5 bits, okay? The carry here, I don't consider it as a part of the result. Okay, this may be true, or you can consider it a part of the result in case of numbers, if you consider numbers. But if it is hardware circuit and you have a circuit for 4 bits or 5 bits added to a circuit of 5 bits, and then the result is stored in 5 bits, in this case, this one is not a part of the result. Okay, resulting means the output of the circuit. Anyway, so in case of 5 bits, what is the limit you have here? It should be, as I said, from 0 until 2 to the power of 5 minus 1, which is 31. So that means I can store numbers from 0 to 31 nicely. And you can see here all the numbers here. You can see here all the numbers here. This is for 0 all the way until 31. Is that okay? By the way, if you have 1, 1, 1, 1, and then you add 1, you actually jump to 0, 0, 0. Okay? So if you have here 1, 1, 1, 1, 1, and then you add 1, so you are going to get 0, 0, 0, 0, and then you have a carry here. Okay, so you cross. So this is when overflow happens. If you add, listen to me, if you add number to a number and you don't cross this limit here between, you don't cross from here to here, actually there is no overflow. So let's do it here. For example, 28 plus 6. Okay, if you add 28 plus 6, this is 28 and this is 6. So I'm gonna add it. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0, and then we have a carry here. 1 plus 1 plus 0 is 0, and then we have 1 here. 1 plus 1 and 0, I'm going to get 0, and then we have carry here. Carry. So this is the result. So I added 28 plus 6, and this is the result I got. The result is 2. The result is 2. Okay. For sure that's wrong. Because, and how I can know if there is overflow? You don't need to do conversion, please. Because you are going to waste your time in the exam. Okay. So this is a bad way to do it. You just to convert it and see if the result is good, but this is waste of time. The easier way to do it, as I'm explaining here, if there is a carry resulted from the last bit, so there is overflow and the result is not correct. Okay, don't be confused. This carry is not a part of the result. The result here means I add 5 bits to 5 bits, I got 5 bits. Okay, so and this is very obvious here, because if when you add 28 plus 6, you are going to get 34. right? But I told you the limit is 31. Okay, so I need bigger space. 5 bits are not enough. I need one more. Okay, so actually what happened, I added 20, this is 28 here. Okay, and then I added 6. 1, 2, 3. This is the problem. I crossed from 1, 1, 1, 1 to 0, 0. Okay, that's why I come to 2 here. Did you see how I got 2? I got 2 because when I started from 28, okay, and then I added 6, I came to here. Because after 1, 1, 1, 1, 1, I'm going to get 0, 0, 0, and there is a carry. Okay? So in exams, and 100% this will be in quiz, in test, in everything, I will ask you. What I'm going to do is, I'm going to give you 2 numbers. I have to tell you if this number signed or unsigned, okay? And then I ask you if there is overflow or not. That's it. So all what you have to do normal addition in case of unsigned. Do normal addition. If there is a carry resulted from the last bit, so there is overflow, okay? Here, in case of signed number, as I told you, if you add 2 positive number and I get negative number, or if you add 2 negative number and you get positive number, okay? This is one way to, any other case, okay? There is no overflow, okay? So if you add 2 positive, you got negative. If you add 2 negative, you got positive, okay? So for example, here I am telling you these numbers are signed, okay? So here I'm adding 12 plus 5, okay? So if you add here, 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 0, and then we have 1 here, 1 plus 1 is 0, and then we have here, this is the result I got. So if you look here, this is a positive number, I added to positive number, and then I got a negative number, okay? So that means I don't need to do conversion. I'm just doing conversion just to convince you it is wrong, okay? So don't waste your time in exams to do conversion, to convert. So here, this is 12 plus 5 is actually 17. But because the limit, how many? 1, 2, 3, 4, 5. So the limit here for the positive numbers is 2 to the power of n minus 1 minus 1, which is 2 to the power of 4 minus 1, which is 15. So the limit here should be positive 15, as you see here, positive 15. Now I need 17. That's why I exceeded the limit. That's why I got wrong result this here. Okay. So what happened here to end this lecture? Okay. So as you see here, guys, this is positive numbers are here, and negative numbers are here, and the boundary is here. Boundary. Okay. What happens is that if you add 1, if you are 15, 15 means 1, 1, 1, 1, 0. Okay. And then you add 1 to 15. The hardware, look how it is going to be how the hardware will do it. 1 plus 0, and then we have 1, 0, 0, 0, 1. So the hardware is going to cross this boundary here. Okay. So if you add 15 plus 1, the hardware will give you negative 16, because you add bit to bit. So every time you create this boundary, so what I did here exactly, I started from 12, so I was here, and then I added 5. 1, 2, 3, 4, 5. Because once it is 15, if you add 1, you are going to jump to here. You are going to come to here. Okay. So to end this lecture, it's very simple. I'm expecting you understand what I mean by overflow. Okay? And because the hardware, you have any bit, I'm going to add it to any bit, and then the hardware has any bit, the result. Okay. So you understand what overflow means. More importantly, you should know, if I give you numbers, you should know how can you know if there is overflow or not. Okay. The way you have to do it, in case of unsigned number, you can do normal addition, and then if there is a carry resulted from this one, so there is overflow. If there is no carry, no overflow. But in case of signed numbers, still you can do normal addition. But now, all what you have to do, you have to look at the sign. This is positive plus positive, I got negative. Or negative plus negative, I got positive. This is the only 2 cases. Any other case, don't think about it. It's done. The only case when you add positive to positive. Yeah, for example, if this one is 1 and this one is 0, you don't even need to think about anything. This is a negative number and this is positive number. It's impossible to make overflow. Overflow happens when they have the same sign. when they assist each other. Okay, I think that's enough for today. Thanks, guys. Bye.